For our inferences about our intercept, we want to first take a look at the sampling distribution of that intercept, and we come back that once again the expected value of our estimator is going to be equal to the true value. That's good, it's unbiased. And then the standard deviation is going to be equal to a slightly different expression than we had before. Go back to that standard deviation of the error times now the square root of 1 over n plus x bar squared over s sub xx. Right, that's a different kind of form than what it looked like before. And notice that the larger n becomes, right, the more that term goes away. But that's not the whole aspect of this guy right here. So that's a crucial change in difference than what we saw before. And then finally that beta naught is normal follows again from our underlying distribution of the error term to begin with, its assumption, and then that beta naught is ultimately a linear combination of a whole lot of other things that were ultimately got us back to the normal kind of situation, right? Now, one of the key things here then in developing inferences and say the confidence intervals are going to be that we're going to come in and we're going to estimate this value, okay, and we'll call that S beta naught. Right, your textbook will use SE beta naught. I like this notation, doesn't really matter, but we're going to come in and we're going to substitute for this guy right here the standard deviation of the error that we found in our data, and then 1 over n plus x bar squared over s xx. Well, the rest of it's the same as before, so we're substituting in differently right there, and that's the big thing. So that means when we come down here for the confidence interval for beta naught, because we made that substitution, then we end up with the t-distribution right, and that's over s beta naught, and that has n minus 2 degrees of freedom just like before. And so we're going to go develop the, once again, the 95% confidence interval, two-sided, for beta naught, and see what that develops for us. Our beta naught value that we calculated for that aquifer data was 1.3098, right? Actually more digits, but that's good enough for now. And then our standard deviation is 0.912. That's your standard error term, and then times the square root of 1 over 17 plus our mean of the x values, 13.31 squared divided by 79.1. So note that the 1 over n term is going to actually be somewhat negligible. It's not going to influence the overall term under the radical in this case. And that will give us a standard deviation term there of 1.3826. Right? And so coming back from our t-test, the 95% confidence interval, n minus 2 or 15 degrees of freedom, that t critical value 0.02515 is the same as it was before, 2.131. So when we go to create the confidence interval, that'll be beta naught hat plus or minus our t critical value times our standard deviation term. So that'll be your 1.3098 plus or minus 2.131 times 1.3826. Right, and that's going to lead us to an interval that is fairly broad here for our intercept value, negative 1.6 4.6366 up to 4.2562. Remember, by the way, that these are thousands of acre feet of volume of water. So that's also something important here to remember here. For the big picture for us, note that this interval contains the special number of 0. And the intercept value in this case says something about the storage that might actually be in the aquifer, because remember, we got water going into the system, water going out of the system, and one of the things that might be of interest is, well, what might be the situation if we have a drought that's so severe that we have absolutely no water coming into the aquifer. What might we expect the discharge to be, and what's that doing to our storage in that particular case? And you could link that with climate change and all those sorts of things. We won't go down that particular path, but we will go after here as our null hypothesis then that we'll look at the case of beta 0 being 0, and our alternative could be one-sided, but we're going to go ahead and just continue with the two-sided and look at the 5% significance level. We could have turned that to be something different as well, but you'll see it's not going to ultimately be all that important to us. Our test statistic is similar to what it was before. We're going to have a t-distribution. I have beta hat 0 minus the beta 0, the true parameter from the null hypothesis value. That was this guy right up here. And divide by our standard deviation. Right, just as nice and simple as that. Our calculated t-value then is going to be 1.3098 minus 0 over 1.3826, or 0.9473. Right, and our t-critical value is, once again, for two-sided 95%, or rather 5% divided out by 2 into the two tails, and that's still 2.3131. And so our t naught value is less than our t critical, therefore do not reject our null hypothesis. Right, now the p-value that went along with our calculated statistic value is slightly different than it was before, although when you round it, it turns out to be also about 36%. Right, so in this case, there's we do not reject the null hypothesis here that the intercept is 0. We could tighten this up and look at a different kind of hypothesis and that sort of thing, but and just exactly what the physical significance is of this intercept being 0 is of some question. We need to think about more carefully about what we're really modeling and what the connection is between this estimated recharge versus the discharge. And the other thing to keep in mind from a physical practical scenario here about whether this statistical model is even appropriate or adequate is that if we were truly looking at the water that was coming into our watershed in that one particular year and the water that gets down into the aquifer, well, the time that it takes for that to happen, that infiltration, that percolation, is fairly extensive depending on how deep that aquifer is compared to the surface and what the communication paths are in between. And as such then, we have to be very careful how we might begin to interpret these numbers and what we want to think about. And that's one reason why you see this having been posed as the estimated recharge, and jointly matching that up with the discharge values in that particular year. This is in that physical scenario, there's a far more complicated physical scenario or communication or functional relationship that's happening than is revealed entirely only by the linear regression model. And so it's just another example of how you can potentially misuse these relationships and the hypothesis tests conclusions that we get out of it. You have to be very careful and thoughtful about what all these numbers mean and be circumspect in their use.